It feels like you can't ever stop learning in machine learning research, right?
Yeah.
Especially in fields like embodied AI and robotics. Where the lines between the virtual and real world start to blur.
Yeah.
We actually came across this new paper, and we thought you might find it interesting. It tackles a really fundamental problem in this area.
Yeah.
So instead of you having to read the whole thing yourself, we thought we could walk you through the core ideas.
Yeah, think of it like a guided tour of some really cutting-edge research.
Perfect.
Today, we're diving into this new benchmark called MOE.
MO?
Yeah, it stands for Embodied Mobile Manipulation in Open Environments.
Oh, okay.
The researchers basically created a way to comprehensively measure how well robots can actually do those everyday tasks that we describe using natural language.
Interesting.
And, those longer duration tasks, not just like pick up the cup.
Yeah, the really complex stuff.
Right. And all our insights today are coming straight from the MOE paper itself.
So what are we trying to achieve with this deep dive?
Yeah, good question.
Why do we even need a new benchmark like MOE right now? What's so new about it?
Right.
And I guess, what does all this mean for the future of Embodied AI?
Yeah, let's get into it. So the paper we're looking at is called, and this is a mouthful, MOE, a comprehensive benchmark for embodied mobile manipulation in open environments.
Wow, that is a long title.
I know, right?
Uh-huh.
But the authors, right from the get-go, they point out this big disconnect we have. Current embodied AI evaluation, it doesn't actually assess the kind of complex activities that we imagine, for truly intelligent robots.
So like the robots we see in sci-fi movies.
Kinda.
That can understand and actually do what we tell them over a long period of time.
Exactly. That's the disconnect they are addressing.
It sounds like we aren't really measuring progress as well as we should be.
Yeah, and that's where MLE comes in.
So what are the limitations of how we do it now?
Right, so there are a few things. The paper highlights them pretty clearly. Like traditional machine learning techniques, things like imitation learning and reinforcement learning, those have worked great, for teaching robots specific isolated skills.
Yeah, like grasping a specific object.
Exactly.
We see robots do that all the time now.
Right. But these methods, they struggle when you throw tasks at them that require like a whole sequence of actions.
What if the environment changes even a little?
Exactly. They don't generalize well.
Uh-huh.
And then there's TAMPI.
Remind me, what is TAMPI again?
Oh, it's task and motion planning. It tries to handle longer, more complex tasks.
Okay, great.
By breaking them down into individual steps.
But I feel like even that needs pretty specific goals.
You got it. It needs very specific
It needs
goals.
structured environments.
Yeah.
The real world is so much messier than that.
Yeah, that's the problem.
And let's be honest, human instructions, sometimes they're not very clear, are they?
Not at all, haha.
If you tell a robot to make the kitchen look nice, that's a lot for a robot to process.
Oh, absolutely.
How does it even begin to turn that into actions?
It's tough. And the paper really dives into this. The real world, it's constantly changing. And then you add on top of that how vague human language can be. It's a huge challenge for our existing machine learning methods to deal with.
Oh, yeah, that makes sense. So we have these problems, but why is now the time for MOE?
Right.
I know the paper talks about this why now aspect.
It does. And it boils down to recent advancements in two big areas of machine learning, LLMs and embodied intelligence itself.
Okay, LLMs, those are large language models. We've talked about them a lot on the show.
Yeah, exactly.
They're the ones that are revolutionizing how we deal with high-level reasoning. They can understand and generate natural language better than ever before. And they're even getting good at processing visual information.
Yeah. So we have this incredible progress on that front.
And on the embodied intelligence side.
Well, we've seen significant progress in low-level robotic capabilities. Things like navigation.
Getting around.
Yeah. And manipulation, so how they actually interact with physical objects.
So like grasping and moving things.
Exactly. So robots are getting much better at actually moving around and interacting with the physical world.
It sounds like we have all these amazing individual pieces.
We do.
The LLMs for thinking and the robots for doing. But the challenge is putting them together.
That's exactly the gap that this paper is addressing. We see great progress in all these individual tasks within embodied AI, like using LLMs for planning, vision models for understanding what the robot sees, and better robot movement and grasping.
But there isn't anything to bring it all together.
Right. We're lacking a benchmark that tests how all these different machine learning capabilities actually work together.
When they have to do a complex multi-step task.
Yeah. Plus, existing evaluations, they often use very specific simulated environments.
Or scenarios that are totally scripted.
Exactly. And that doesn't reflect the real world at all.
Right.
Our machine learning models need to be able to handle the messiness of the real world.
So the paper talks about this concept of LLM grounding. Can you explain that a bit?
Of course. Basically, it's about connecting an LLM's understanding of language with the actual physical environment, and then getting the robot to do something in that environment.
So it's not just about understanding the words, it's about translating those words into actions.
That's it. And it's a really tough problem. If you tell a robot to put the blue cup on the table.
That seems simple enough.
You'd think so.
Yeah.
Right. But the LLM needs to be able to actually identify which cup is blue and where the table is.
In its environment, right?
Exactly. And then it needs to figure out how to actually move to the cup, pick it up, and put it on the table.
Wow, yeah, that's a lot more complicated than it sounds.
It is. And that's why LLM grounding is such a big challenge in machine learning right now.
So MOE is designed to deal with this, right?
Exactly. MOE wants to be the benchmark that really addresses this integration challenge.
So what does MOE actually involve? How does it evaluate these systems?
So imagine a unified benchmark where agents, those are our robots essentially, have to interpret instructions given in natural language.
Like the kind of language we use every day.
Exactly. And then they have to perform these complex everyday tasks in a continuous environment.
So it's not just one specific isolated skill.
Nope. It's about putting everything together.
And how do they evaluate this?
MOE's big thing is that it integrates the evaluation of both high-level reasoning, which is where LLMs come in, with the low-level stuff.
The navigation and manipulation skills.
Exactly. It's all about how these different parts of the system work together.
It's a more holistic approach.
Yeah, exactly. And the paper outlines 3 key contributions MOE makes.
Perfect. Let's hear them. What are the main things that machine learning researchers should take away?
So the first one is obviously MOE itself, the benchmark we've been talking about.
The unified benchmark for evaluating those high-level and low-level tasks.
And it comes with 3 brand new evaluation metrics designed specifically for these integrated tasks.
Okay, interesting. We'll have to get to those.
We will. The second big contribution is the MOE 100 dataset.
What is that?
It's a brand new collection of 100 complex everyday tasks.
Okay.
And the really cool part is that it includes detailed process annotations. It's like step-by-step reasoning, but for robots.
Like a chain of thought, but for a robotic agent.
Yeah.
So it's not just a bunch of actions and outcomes.
Right.
It's about the reasoning behind the actions.
It really is. And the data set includes a wide variety of task designs.
To make sure the models are really challenged.
Yeah. And they even included examples of how an agent might replan its actions if something goes wrong.
Oh, that's smart. So the models can learn to be more robust.
That's the idea.
Yeah.
And this is really important. It includes sub-data sets that are formatted specifically for training and fine-tuning LLMs for these embodied tasks.
Oh, so it's really tailored for this kind of research.
It is.
You said there was a third contribution.
I did. The third one is Homeybot.
What's that? Another data set?
It's not a data set. It's an actual agent system.
Oh, okay.
The researchers developed it to show how MOE can be used in practice.
Cool.
It combines a fine-tuned LLM, specifically a version of video LLM, with lightweight navigation and manipulation models.
Yeah.
And it's got these error detection mechanisms built in.
Oh, that's interesting. So it can identify when things aren't going according to plan.
Yes, exactly. And that feedback helps it improve its decision-making.
I like it. So tell me more about this MOE 100 data set.
Sure.
You said they used fetch robots and the Habitat Lab 2.0 simulation platform to collect the data.
Yeah, that's right.
Why is that important for machine learning?
Well, they used these fetch robots in simulated environments made with Habitat Lab 2.0. And that gave them a data set with, get this, 966 subtasks.
Wow, that's a lot.
Yeah. And for each one, you get a predefined action.
Okay.
Target object or location. Which low-level model should be used.
Okay.
And images from the robot's point of view.
Really?
Oh, and those detailed reasoning processes we talked about.
I like that they are providing all of that. It's really comprehensive.
It is. And using a well-established simulation platform like Habitat Lab 2.0 means that other researchers can easily reproduce their work.
That's really important for machine learning research.
It is.
Can you give us an example of one of these tasks? I want to get a sense of what these challenges are like.
Yeah, of course. One example from the paper is, check if there are any bananas in the fridge. If not, take one banana in the kitchen and put it in the fridge.
Okay, that makes sense. It sounds pretty realistic.
It does. And the authors point out that the reasoning process is a really important part of this.
What do you mean?
So the agent has to check the fridge first. Even if it gets a banana from the kitchen and puts it in the fridge, if it didn't check the fridge first, it failed.
It's not just about the end goal.
Right. It's about following the right steps.
Which makes sense.
Yeah. And the paper says that these 100 tasks, they have all these different attributes. Some are short, some are long, some are open-ended, some require logical reasoning, and some are designed to sound like how a human would actually talk.
Oh, that's cool.
Yeah. So they are really testing these models in all sorts of ways.
So it's clear that MOE 100 is a really valuable resource for machine learning research.
That is.
It's not just a bunch of basic actions. Now, you mentioned that MOE uses these new evaluation metrics. Why are the traditional metrics not good enough anymore?
Yeah, so traditional metrics like simple success rate, which just tells you if the task was completed or not, or goal condition success, which checks if the end state is correct, those are too simplistic.
Especially for these longer, more complex tasks.
Exactly. They don't tell you anything about how efficient the process was, the reasoning involved, or if the agent could recover from mistakes. And those are all crucial things for truly intelligent behavior.
We want our robots to be smart, not just lucky.
Exactly. And for MOE, which is all about understanding language and being flexible, the old metrics just don't cut it.
So what are these new metrics?
Well, there are three.
Okay, let's hear them.
The first is task progress, or TP for short.
What does that measure?
It measures the entire execution process, from start to finish.
Okay.
And how the different subtasks are connected. It compares what the agent actually did to these predefined key paths.
What are key paths?
Those are the essential subtasks that need to be done to achieve the goal.
Got it.
But here's the cool part. TP rewards agents that can reach the goal even if they deviate from the plan, as long as they do those key steps.
So it's okay to be flexible.
Exactly. Because in the real world, things don't always go according to plan.
So TP is about evaluating the quality of the problem-solving process, not just the outcome.
Exactly. The second metric is success end rate, or SER.
What does SER tell us?
SER measures how well the agent can figure out when a task is actually finished.
You mean knowing when to stop?
Yeah.
That seems important.
It is. A truly intelligent robot shouldn't just keep going and going, even after it's done what it was supposed to do.
So SER is about accurate decision-making.
And the third new metric is Success Replan Rate, or SRR.
Okay, what's that one about?
This one measures how well the agent can adapt when things go wrong.
In the real world, things go wrong all the time.
Yeah, it's inevitable.
Sure.
So the agent needs to be able to recognize when something has failed, figure out why, and come up with a new plan.
So SRR is about being robust and adaptable.
Yeah, it's about being able to deal with the unexpected.
These new metrics sound much more useful for evaluating these complex tasks.
They are.
So let's talk about Homeybot, that agent system you mentioned earlier.
Okay.
What's the machine learning behind it?
So it's a hierarchical framework.
Okay.
It has two main components, a high-level planning component called HLP and a low-level execution component, or LLE.
Got it. What does each part do?
The HLP, which is driven by that fine-tuned video Alavi model, takes the user's instruction and breaks it down into smaller, more manageable subtasks.
So it does the planning.
And it can adapt the plan based on what's happening in the environment.
So it's constantly learning and adjusting?
Right. Then the LLE takes those subtasks and actually executes them using a bunch of lower-level control policies.
So it's the one interacting with the environment.
Yeah. And after each subtask, it reports back to the HLP and lets it know what happened.
So they are constantly communicating.
They are. It's a continuous loop.
What kind of information does the HLP use to make its plans?
It gets a ton of information.
Okay, tell me.
It gets images from the robot sensors, information about the system, like battery level, and the original instruction from the user.
Oh, wow.
Yeah. And it also knows what objects the robot is holding, what actions it has already taken, and any feedback from the last subtask.
It sounds like it has access to everything it needs. It does. And it uses all this information to generate an output that tells the LLE what to do next.
And that output is formatted in JSON.
Yep, exactly.
So it's standardized.
And what about the low-level execution side?
Yeah, what kind of machine learning models does it use?
So there are two main settings for that.
Okay.
And one, the low-level models have access to information that a real robot wouldn't have, like the exact 3D location of every object.
Oh, so it's like cheating a bit.
Kind of, yeah.
Yeah.
In that setting, they use a model called M3, but they also wanted to see how well the agents would perform without that extra information.
More realistically.
Yeah, using only the data that would be available to a real robot through its sensors.
Makes sense. So what models did they use in that case?
In that setting, they used a bunch of lightweight models.
Like what?
For manipulation, like picking up and placing objects, they use RT1X and Octo. And for navigation, they use Nomad and PixNav.
And those are all lightweight models.
Yeah, they are. Which is important if you want the robot to be able to make decisions in real time.
Oh, yeah, that's a good point.
Because you don't want the robot taking forever to process everything.
Ah, that's true.
So they really wanted to see if these lighter weight models could handle these complex tasks.
You mentioned earlier that Homeybot has this error detection system.
It does.
Can you explain how that works?
Yeah, so it's designed to catch 4 main types of errors.
Okay.
Logical errors, like trying to pick up something when the gripper's already full. Distance errors, like being too far or too close to an object. Format errors, where the HLP outputs something that doesn't make sense.
Okay.
And execution errors, which happen when the low-level models themselves mess up.
So it's pretty comprehensive.
It is. And it breaks down each of those main types into more specific subtypes.
To give the HLP as much information as possible.
Right. So the HLP can understand why something went wrong and adjust the plan accordingly.
Okay, so they built this benchmark, they built this agent, and they ran experiments.
Yeah.
What were the main findings?
So they used data augmentation techniques to train the HLP, things like SFT and DPO, and they compared Homeybot to other state-of-the-art models. And the results were pretty impressive.
Really?
Yeah, Homeybot, especially the version trained with DPO, did the best on many of the MOE metrics.
So it beat the other models?
Yeah, including models like GPT-4o and Gemini 1.5 Pro.
Wow, those are some pretty powerful models.
Yeah, they are. And it beat them on metrics like success rate, path-length weighted success rate, and task progress.
That's pretty convincing evidence that their approach is working.
It is. And it shows how valuable the MOE benchmark is.
Did they find anything surprising in the results?
They did, actually.
Oh.
Couple of things.
What were they?
First, the SFT version of Homeybot actually had a better SRR than the DPO version.
Interesting. You'd think DPO would be better at that, right? Since it's specifically designed to learn from preferences.
You would. But the authors think this might point to some problems with how DPO generalizes. Maybe it's too focused on the specific failures it saw during training.
And it can't adapt as well to new, unexpected failures.
That's the idea. They also found that the SCR was very consistent across both the training and test sets.
For Homeybot?
Yeah.
Which means?
Well, it suggests that being able to recognize when a task is done might be more about the model's core reasoning abilities than the specific training data.
Oh, that's interesting.
And when they looked at the LLE specifically, they found that the pick action had a lower success rate than other actions.
Oh, so picking up objects was still tricky.
Yeah, it seems like there's still room for improvement there. And not surprisingly, open-ended tasks were the hardest for all the models.
Yeah, those are always the most challenging, right? Because there are so many ways to approach them.
Exactly.
So even with Homeybot, there are still challenges to overcome.
Definitely.
Did the authors talk about any limitations of the MOE benchmark itself?
They did. They pointed out a few things.
Like what?
Well, the habitat simulator, the one they used to collect the data, it has some limitations, like the types of actions the robot can do and the size of the environment.
So the tasks can't be too complex or too varied.
Right. And while the standardized JSON output from the HLP is good for comparison, it might also mean that we lose some subtle information.
Oh, that's a good point.
And Homeybot, because it has this hierarchical structure, it can be computationally expensive.
All those models talking to each other?
Yeah, exactly. And of course, there's the ongoing challenge of transferring these models from simulation to the real world.
Which is a problem for all of robotics, right?
It is. Simulators are great, but they can't capture everything about the real world.
So what's next? Where do we go from here?
Well, the authors suggested a few things.
Okay, let's hear them.
One is deploying the system in the real world and collecting real data.
Oh, getting out of the simulator.
Yeah. And that's one of the great things about their work, the data collection methods and metrics. They're designed to work outside of the simulator. Another area they want to explore is using historical visual data more effectively.
So not just text, but images and video.
Exactly. So the agent can learn from its past experiences better.
And the last thing?
They want to look more into how these agents can interact with humans.
You mean in a collaborative way?
Yeah. so the robots can actually be helpful in our daily lives.
This all sounds very promising. It feels like a big step forward.
It does.
But I want to take a step back for a second.
Okay.
Where does MOE fit in the big picture of machine learning and robotics?
Good question.
We've been trying to build robots that can understand us for a long time.
Oh yeah, this has been a goal for decades.
What's changed?
Well, early research was all about task-specific policies.
Using methods like imitation learning and reinforcement learning.
Yeah, but those approaches were very limited.
They couldn't handle anything new.
Right. Then came TAMPI, which was better at planning, but it still had problems with the messiness of the real world.
And then LLMs came along and changed everything.
They did. LLMs have really revolutionized what we can do with language.
So MOE is building on all that.
It is. It's addressing the new challenges that LLMs have brought to robotics.
I know the paper mentions some other embodied AI benchmarks.
Yeah, in the appendix, they talk about things like LFRED, Behavior 1K, and OVMM.
What makes MOE different?
MOE focuses specifically on long horizon tasks, those that require extended planning, and it really emphasizes how high-level planning and low-level actions work together.
It's about integrating all those different pieces.
Right, and it introduces these new metrics that give us a much more detailed understanding of how well these agents are performing.
So it's a more comprehensive and rigorous benchmark.
It is.
So just to be clear, MOE is a big deal because it's pushing the boundaries of how we evaluate these embodied AI systems.
Exactly, especially for those tasks that are driven by language and require a lot of planning.
And the data set they created, MOE 100, that's a really valuable resource.
It is. It gives us not just the tasks, but the reasoning behind them and how to recover from failures.
And the new metrics, TP, SER, and SRR, they give us a much better understanding of how well these agents are doing.
They do. It's not just about passing or failing anymore.
It's about how they are thinking and adapting.
Exactly. And why is all this important?
Yeah, why should people care about this?
Well, the end goal is to create robots that can actually be helpful in the real world.
To help the elderly, people with disabilities, or just to do chores around the house.
Exactly.
And benchmarks like MOE are crucial for making that happen.
They help us measure progress, identify where we need to improve, and ultimately create robots that can understand us and help us.
So it's all about translating all this machine learning progress into real-world applications.
It is. Now for our Novel Notions segment.
Where we explore some new ideas based on this paper.
Right.
What are your thoughts?
Okay, so I was thinking MOE has all these complex tasks, right? But what if, instead of throwing all of them at the model at once, we create a curriculum of complexity?
What do you mean?
Like we start with the simple tasks, then gradually introduce more complex ones.
So the model can learn the basics first.
Exactly. Just like how humans learn.
We don't start with calculus.
Right, haha. And I think this could be really helpful for understanding how different models learn and what their limitations are.
So we could see if certain models are better suited for certain types of tasks.
Yeah. And it might even help us develop better training methods.
It's an interesting idea.
What about you? What are you thinking?
Well, one of the limitations we talked about was the gap between simulation and the real world.
Right. That's a big one.
So I think it would be really interesting to extend MOE to include more realistic environments.
You mean getting rid of the simulator?
Well, not necessarily getting rid of it, but making it more like the real world.
Okay, I see.
Like including real world sensor data and maybe even having humans interact with the robot.
That would be a real challenge.
It would, but I think it would be really valuable.
Yeah, if we want these robots to actually work in our homes, they need to be able to handle the unexpected.
They need to be able to deal with clutter, with things moving around, with changes in lighting.
All the things that make the real world so messy.
Exactly.
And that's where benchmarks like MOE come in.
They can help us push the boundaries of what these systems can do.
So MOE is a big step forward in embodied AI.
And it gives us a lot to think about for the future.
It does. For those of you who want to learn more, we'll link to the paper in the show notes.
Absolutely. And for now, I think this is a good place to wrap up.
Yeah.
As always, thanks for joining us.
It's been a pleasure.
Until next time.